Uh, shall I speak first or the organizers?
No, just according to the timetable, the schedule
Okay.
initiate.
Okay. So, respected speakers, guests, and participants, a very good morning to you all. Now, this new normal situation during this COVID-19 pandemic, I really welcome you all in this virtual platform of KC College, Brahmananda Keshab Chandra College, at the national webinar on quantum and particle physics. We are extremely honored to have our collaborators from the Academic Trust, IISc Bangalore. I welcome today's eminent speakers who will enlighten our students and faculty and also enrich their knowledge in the subject of physics.
Madam,
I
please start
sincerely
your
hope
video.
that the participants will be greatly benefited by this national webinar on physics. I thank the organizers again for arranging this webinar. Thank you and welcome all of you. Thank you, sir. I welcome our eminent speakers, Professor Shushanto Dattagupta and Professor Shubhavati Goswami, who will enlighten us with their knowledge on physics. And I also welcome my collaborators from the Academic Trust of Bangalore. Thank you.
Thank you, Madam Principal.
Thank you. Welcome.
Now I request Professor K.B. Sinha to start the introduction of the first guest lecture. Just unmute yourself, sir. Sir, please start your microphone. Okay.
Okay. So can you hear me now?
Yes.
Yes.
Okay. Now, I'd like to welcome all the speakers and Madam Principal and Dr. Roy as well as Shubham Kaur Biswas for making this possible. And I would like to say a few words about the Indian Academy of Sciences as well as the Academic Trust. The Indian Academy of Sciences was established in 1934 by Professor C.V. Raman, and the Academic Trust was set up in August 2014, a bit less than a century later, under the auspices of the Indian Academy of Sciences. One of the major goals of the trust is to organize events like this to bring about a tangible change in the way science is taught and implemented in the educational system in India and society in general. Unfortunately, COVID-19 intervened, so we could not hold these events as a physical event, and we, as we would like to do, that's why we had to take these platforms, use these platforms for continuing this work. This is so we have already had, I think, 4 webinars, and these are the 5th and 6th webinars under this series, in this series. Let us again welcome the 2 speakers today, both distinguished physicists and practicing in different areas of physics. The first speaker today is Professor Subhrabati Goswami, who is a professor in the Physical Research Laboratory in Ahmedabad. And her research interest lies in high energy physics, more specifically neutrino physics. And Professor Goswami is a fellow of this academy, that is the Indian Academy of Sciences, as well as the other national academies, and is a J.C. Bose Fellow. Today she will speak on neutrinos, the invisible messengers from the space. I will postpone my introduction of the second speaker, Professor Dattagupta, whom I know for many decades, till just before his talk. So I think we can now begin with the talk of Professor Goswami.
I have to share the screen, but it is saying host disabled attendee screen sharing.
Manoj, can you hear me? Manoj?
Excuse me, Subha, I cannot, Manos cannot hear you probably, but I think please request everyone.
Okay, okay, I'm just requesting the host to make Professor Goswami as a co-host. Please do it immediately.
I think Principal Madam is now host.
Okay.
Madam, please.
I think Manos or Subhankar, please request everyone to mute their microphones.
So, excuse me, Madam, please make our speaker co-host. You are now host. Madam, you are now host. You are muted. You are muted now. Please unmute.
Where should I do it? Where should I do it?
Now you're okay, ma'am.
Samosa is doing.
I am not able to share the screen because of this issue. Am I your host?
Madam?
Yes, how tell me how to do it.
Just
click on
just
her.
click the,
Just click on her name.
In the top, you will find.
Find participant.
Shall I go out of this?
No.
No,
Just
no,
go
ma'am.
to
Yeah,
the
you can make
participant list. Go to the
anyone of
participant list.
host, or you can make any one of us host,
Okay,
so
okay.
that we can do it.
The participants and then
Then search her name,
yeah, got it.
and then in the more option,
Made it.
just make
Okay,
it.
I made it.
Thank you, ma'am.
Now, madam, you can share your screen.
I will try. Yes. Just a second.
You made her host.
Madam, now you can share your screen, ma'am.
Yeah, I can try. Is it fine? Can you people see?
Yes, ma'am. Visible.
Yes, we can see.
Perfectly visible.
Okay, so just 1 second. I will start. Just 1 second. I am really sorry. One of our students is unwell. He had to be hospitalized, so he was calling. So I just had to send her a message, and that's I got little delayed. Okay, I would like to thank the organizers very much, Professor Sina, Professor Chakraborty, and the other organizers, and also Professor Partho Mojumdar, President of Academy, for asking me to give this talk. It's really a privilege for me to be here and share the platform with Professor Dr. Gupta. I will be talking on neutrinos, the invisible messengers from space. So, yes. So, our interest in space perhaps starts from our very childhood. Many of us are doing research, many of us are may not be doing research, but I think our interest for the stars and the moon starts from the very beginning when we learn this twinkle, twinkle, little star, how I wonder what you are. And this is a quote from ancient philosopher Socrates, who said that man must rise above the earth to the top of the atmosphere and beyond, for only thus he will fully understand the world in which he lives. I think this sets a nice background for the kind of studies, the work that I am going to present. So, astronomy is a natural science that deals with the study of celestial objects and phenomena that originate outside the atmosphere of the Earth. So, we have many ancient astronomers. It is a very ancient subject. And for instance, I have given photos of three ancient astronomers, Hipparchus in Greece, who worked on motion of sun and moon, and at that time they were all called philosophers, mathematicians, astronomers. There were not so much specialization as of now. Then there is Hypatia, who was a he was a it's very noteworthy that at that time she was a woman astronomer and mathematician, and she did work on charting of celestial bodies. And then Aryabhatta from India, who was is also we know very well. He is a famous mathematician, and also he worked on motions of solar system. So to see far, we need something, because we can see something in our with our eye only, but to see more and to see farther, uh, we what is there are telescopes. And the history of telescope, first, that first telescope was about 400 years ago, and it was by Dutch spectacle makers Lippershey, Metius, and Jensen. They had the first telescope goes to the discovery, the or the construction goes to them. At that time it was just kind of a magnifying object, a system which just magnifies a thing a little bit. However, this was greatly improved by Galileo Galilei, and with his telescope Galileo could see many of the things. The first thing that he saw was that the moon had a structure, so the craters of the moon. And then he went farther. He improved his telescope farther, and he saw the sunspots and the moons of Jupiter. So that was all. This was a refractor telescope. That principle is used till now, but of course it is much improved. And however, this was optical telescope, but world, we know now that world is not just what we see in our naked eye. For instance, we can see a rainbow in our naked eye, but there is a full electromagnetic spectrum, starting from radio waves, which have a higher wavelength, to the gamma ray, which has a shorter wavelength. And these are these there are various applications of this electromagnetic whole full electromagnetic spectrum in science, in our life. For instance, you can use gamma rays to probe atomic nucleus, X-rays to probe structure of atoms. We know about X-ray diffraction. Then we use microwave at our home. Then we also use we know the use of radio waves. So in our practical life as well as in the in science, these are very important. And That's why bigger and better telescopes were made to explore the universe in different wavelengths. For instance, here I have put the pictures of few telescopes. This is the optical telescope at NICE Observatory. Then this is the Chandra X-ray Observatory, NASA. It was named in the name of Subramaniam Chandrasekhar, and it was a telescope to detect the X-ray emission from hot regions of universe, such as exploded stars or clusters of galaxies, etc. Then we have the GMRT, the Giant Meter Wave Radio Telescope in Pune, that is in India, and it has also uh, it can observe different astronomical objects in using radio waves. And the Spitzer Observatory in NASA. The Spitzer Observatory in NASA is the infrared. It observes in infrared, and then the CGRO, it observes in the using the Compton effect, using gamma rays. So all these different telescopes are built to study celestial objects in different wavelengths.
Madam, can I interrupt, madam?
Yes, yes.
Madam, actually the slides are not visible proper. I think
Now, can you see the slide now?
we can see the first slide
Oh,
from
so
the
the
beginning.
arrows are not going.
Oh, okay, okay.
No, this is
No, this
this slide you have seen.
no.
Now it is visible, but
Now it is visible. Now it is visible.
earlier it was not.
Okay, so shall I start again? So, I started from saying that, we are interested in space from the learning time of Twinkle Twinkle Little Star, and then Socrates, ancient philosopher, said that,
Swami,
yes.
you please just let the slides run till the point where you stopped.
Okay.
Yeah, and then you continue.
Okay. So can you see now the slide of the electromagnetic spectrum?
Yes,
Yes.
Okay.
Yes, yes, we can.
Yes, yes.
So what I started saying is that the world is just not what we see, and we can use electromagnetic spectrum to view the universe in different wavelengths. And there are various telescopes that are made to, these are some examples, there are many more, to view the universe in different wave scale and gather information. So this is the image of an exploding star, Crab Nebula. Can you see it?
Yes.
Okay.
Yes, ma'am.
This is the Crab Nebula, which is remnant of an exploded star supernova. And these are the pictures that one can see in different wavelengths. For instance, this is the invisible light using the Hubble Space Telescope. This is the Spitzer that I mentioned of NASA. They observed it with using infrared radiation. This is using radio wave. This is using ultraviolet, low energy X-ray, high energy X-ray. So you can see that it can reveal different structures of the Crab Nebula to us, and then one can infer a lot of properties about this from these kind of pictures. So now we talked about the electromagnetic radiation or the light as the messenger. However, it is not the only messenger. By messenger, we mean particles or waves that carry information. Of course, so this in our life also, the messengers play very important role. Telephone, telegram earlier, and now social media. However, in science also, the messengers are important because they are giving us information of distant objects or many other things. So an important messenger is the invisible particle neutrino. This does not interact with light, and it can bring information from deep within stars, unlike light. By which what I mean is that, as I will explain, that neutrinos are much more weakly interacting than light. So the neutrinos can come out faster than the light. So if there is some astronomical object or some celestial object, then the light will get trapped because it will have interactions. However, the neutrino is very weakly interacting, so it can come much faster. So what is a neutrino? Neutrinos are one of the fundamental particles which make up the universe. It was proposed in 1930 by Wolfgang Pauli. And why did he have to propose it? That was because some discrepancy was observed in the beta decay. So in nuclear beta decay, nucleus is going to another nucleus and an electron or the beta particle is emitted. So it was known to be a two-body process, and the energy conservation would say that the energy of the final state particles, the sum of the energy of the final state particle will be equal to the energy of the initial particle, initial nucleus. So what happens is that this should have, if that is so, then the electron should have a fixed energy given by the difference between the energies of the nucleus. So this plots the electron kinetic energy, the spectrum, and it shows that it has a continuous spectrum rather than a discrete spectrum, which is expected from a two-body decay from conservation of energy. So the question arose that whether conservation of energy is valid or it is violated. And in order to save conservation of energy, Pauli proposed that there is a third particle, neutrino, which is sharing the energy. At that time, he called it a neutron. So according to his proposal, the beta decay will look like, apart from the beta particle, there will be another particle which will emit it. Now we know that it's an electron type antineutrino, which is emitted with the electron. And this will carry the share the energy with the electron, which will make this a three-body decay, and it will explain the continuous spectrum of the electron. So the neutrinos were postulated to help in restoring the energy conservation in beta decay. So this was the letter which Pauli wrote, and he wrote that, "Dear radioactive ladies and gentlemen, I have hit upon a desperate remedy to save the law of conservation of energy. There could exist electrically neutral particles that I wish to call neutrons, which have spin half and obey the exclusion principle. I agree that my remedy could seem incredible, but the one who dare can win. Dear radioactive people, look and judge, your humble servant, W. Pauli." Now what happened is he sent this letter in a conference, and he could not attend the conference because he said he had to attend an important ball party. So he could not attend the conference, and he wrote that. And Fermi got interested in this hypothesis, and he gave a theory of beta decay, including the neutrino, and he coined the name neutrino. And neutrino means little neutral one in Italian. So to satisfy all the conservation laws of nature, the neutrinos have to be massless, neutral, and spin half. And because they escaped detection, and then it was thought that it is weakly interacting. And even Fermi's theory also said that it's very weakly interacting. So all these properties make it very difficult to detect them experimentally. That's why neutrino is sometimes called a ghost particle. And Pauli said that I have postulated something which can never be detected. Can you see the slides?
Yes.
Yes.
So, when I am not able to change the slides, at that time there was a problem. Okay. However, this impossible task was accomplished by Rines and Cowan in 1956, 25 years after the neutrinos were proposed. They used antineutrinos produced in nuclear reactors, and they detected neutrinos using a scintillator type of detector. And for this, Rines was awarded the Nobel Prize in 1995. And Nobel lecture of Rines was titled "The Neutrino from Poltergeist to Particle." So that was really, I very much liked the article and the title, because neutrino was really became a particle from a ghost particle after their discovery. So this is somewhat of a history that why they thought of this experiment. So this is what from his Nobel lecture. And he said that the Second World War had a great influence on the lives and careers of very many of us, for whom those were formative years. I was involved during and then subsequent to the war in the testing of nuclear bombs, and several of us wondered whether this man-made star could be used to advance our knowledge of physics. For one thing, this unusual object certainly had lots of fissions in it, and hence was a very intense neutrino source. So they wanted to use this, this nuclear bomb to some good use. However, later he thought that because there is uncontrolled fission, he should use the nuclear reactors, and he informed these both ideas to Fermi, and Fermi wrote to him that, "Dear Fred, thank you for your letter of October 4th by Clyde Cowan and yourself. I was very much interested in your new plan for the detection of the neutrino. And he said that the new method should be much simpler to carry out and have the great advantage that the measurement can be repeated any number of times. And he said he will be very interested to see the results, know the results. And then this historical telegram was sent to Pauli by the scientists that we are happy to inform you that we have definitely detected neutrinos from fission fragments by observing inverse beta decay of protons, and the observed cross-section agrees well with the expected one. So this is the history of the neutrino, the discovery of the neutrino. And this is the electron type of antineutrino, which is emitted with the beta particle. We also now know that electrons have the antiparticles which are positrons, and the neutrino will be emitted in association with a positron, and the antineutrino will be emitted in association with an electron. These are called leptons, and to conserve the lepton number, this is the kind of association that is seen. And now the question is that whether there are other type of neutrinos also, and the other type of neutrinos were also discovered. And now we know that there are three types of neutrinos: the electron neutrino, which is emitted in association with an electron; a muon neutrino, which is emitted in association with a muon; and a tau neutrino, which is emitted in association with a tau. So I have three leptons and I have three types of neutrinos in association with them. So these neutrinos can come from several sources, both artificial and natural. So the Big Bang nucleosynthesis, which creates the universe. This we have the know about the microwave photons, but they also produce neutrinos. These are of very low energy. Then we have the solar neutrinos and the supernova neutrinos, which are of MeV energy. And also we have terrestrial neutrinos coming from the radioactivity of the Earth's crust, and that is the geoneutrinos. We have the atmospheric neutrinos, which are of GeV energy. And also we can have the man-made neutrinos from reactors, which the Clyde and Cowan experiment had used. And we can have accelerator neutrinos, which were used to discover the muon and the tau neutrinos. Apart from that, we can have very high energy neutrinos, which can come from extragalactic sources. The atmospheric neutrinos come from cosmic rays. And we can have very high energy neutrinos coming from different astrophysical sources. And I will be discussing about these astrophysical neutrinos and the solar and the atmospheric neutrinos in this lecture, not the man-made ones. So the neutrinos are the second most abundant particle in the universe. The cosmic microwave background gives almost 400 photons per cc, and the cosmic neutrino background is 300 neutrinos per cc. And the temperature is about 2 Kelvin. So it is like near the, so this is a very low energy neutrinos which are produced during the Big Bang. So the question is that if we have so many neutrinos, if they are the second most, so much abundant, then why we can't see them? And you know, apart from this, our body receives 400,000 billion neutrinos from sun, 50 billion neutrinos from the natural radioactivity of the Earth, 10 to 100 billion neutrinos from nuclear power plants all over the world. So why are we not able to feel them? That is because they are very, very weakly interacting. So one needs special detectors to detect them. And as I said, a neutrino is detected by observing the product of its interaction with matter. It is very weakly interacting. So the neutrino will produce electron and muon. And what we observe is in the detector is the electron or the muon, which are the charged particles. But since neutrinos are very weakly interacting, we need very big detectors so that we have enough statistics. We need the detectors to be very deep. We have to go often to underground to reduce the cosmic radiation. And also we need a very clean environment to reduce the backgrounds. And for instance, this is the world's largest detector, the neutrino detector, the Super Kamiokande detector in Japan. It is a 50 kiloton detector. And it uses neutrino electron scattering, for instance, to detect the solar neutrinos. And they use the Cherenkov technology, and they have photomultiplier tubes in the water detector. So this is the photomultiplier tube lined along the detector, and these are the physicists of the collaboration fixing the photomultiplier tubes, and you can see the size of the detector from this. So one needs 50 kiloton of water, and with that one has few events per day. So for instance, this is kind of a view graph to show the scale that we have 100 trillion neutrinos per second going through our body, but there will be one interaction in 100 years. But if we have a very huge detector, which is, this kind of a size as compared to the a human size, then there will be about 300 interactions per day. So the question is, if it is so difficult to detect them, then why are we interested in detecting them? So the various reasons are there. For instance, they are information from stars. So this I said that photons will follow a zigzag, but neutrinos will come straight. This is from the sun, for instance. And they pose interesting puzzles, and we will come to that. So there are various reasons why studying these invisible particles is interesting. So the solar fusion reactions that produce heat and light also produce neutrinos, and this occurs through some chain reaction. Pi chain is the main reaction. We also have the CNO cycle, and we have various energy produced through this that ranges from about some MeV to 10 MeV or so, that energy range. And also we have the atmospheric neutrinos, which are produced by when cosmic rays hit.
Something happened, can't hear.
Hello, Professor Goswami.
Yes.
Your video and audio, okay, we can hear you, but your video has gone away. Can you check?
It is saying host disabled attendee screen sharing.
Okay, now we can see you and hear you.
Yes, I am host now. I am making you co-host right now. Please give me some time. Just a minute.
Okay. No problem.
Yes, madam, you are now able to share your screen.
Okay. Okay. So apart from the pi plus, we can also have the pi minus. So we also can have the mu minus and the antiparticle nu mu. Now, these are I would like to mention here that the one of the first detection of the atmospheric neutrinos was in the Kolar gold mine in India in 1965. So we can also have neutrinos, as I mentioned, from supernova explosion. So a supernova explosion is where a star comes to the end of its lifetime. It ends as a supernova explosion of certain mass, and then about 1% of the energy is released in photons, and the 99% of the energy comes out as neutrinos. And this arrives 10 hours before. This can give an early warning of supernova explosion to the various telescopes which are which want to study the supernova explosion. And one explosion, supernova 1987A in the Large Magellanic Cloud, has been observed in the 20th in detectors called Kamiokande and IMB. I will come to this Kamiokande detector later. They observed about 12 to 16 events, and it was a serendipitous discovery. The detector was built for some other purpose, but because the supernova exploded, they observed this few number of events, and a lot of papers have been written, and lot of things have been came to know from few events. So this was a very, very remarkable event, that the recording of the neutrino events from the supernova 1987A. In fact, the Nobel Prize for 2002 astronomy, neutrino astronomy, was given to Ray Davis and Masatoshi Koshiba for pioneering contribution to astrophysics, particular for the detection of cosmic neutrinos. And I will read for the from the Nobel citation. Raymond Davis constructed a completely new detector, a gigantic tank filled with 600 tons of fluid, which was placed in a mine. Over a period of 30 years, he succeeded in capturing total 2,000 neutrinos from the sun, and was thus able to prove that fusion provided the energy from the sun. I will come to this experiment. And with another gigantic detector called Kamiokande, which I already mentioned in the previous slide, a group of researchers led by Masatoshi Koshiba was able to confirm Davis's results. They were also able on 23rd February 1987 to detect neutrinos from a distant explosion. They captured 12, the total of to the 60 neutrinos detector. The work of Davis and Koshiba, unexpected discoveries, and the new intensive field of research, astronomy. So you can see that these were really, really very, very important discoveries, and I will further elaborate on this in the next slides. So the Davis's experiment was the first experiment which detected the solar neutrinos. It started in 1967 and went till 2002. This was pioneered by John Buckle and Raymond Davis from US. And their aim was to probe the solar interior with neutrinos and verify the hypothesis of energy generation in stars. So I said that this PP chain and CNO cycle, and Hans Bethe has given the that how this theory that how the solar energy is generated, and Buckle and Davis thought that okay, let us detect the neutrinos and we can test the solar energy generation hypothesis. So they decided to use chlorine, and they used the procedure was as follows. They used a 600 tons of perchloroethylene, and this was exposed to the sunlight. And the 37 chlorine will react with the solar neutrinos, the electron type neutrinos, which are produced in the sun. In the sun, only electron type neutrinos are produced in the fusion reactions. And this will be absorbed by the chlorine. And then what they will do is they will keep it exposed for some time. Then they will extract it, and then they will extract the argon atom. So they will do a chemical extraction of the argon, and they will study the radioactive decay of argon to get the signature of the neutrino. That's why these are called radiochemical processes. Now, then you have to expose it for days depending on the half-life of the radioactive lifetime, so that the argon should stay as the argon and one can study the radioactive decay of the argon. So they will be kept it for some 30 days or something. I don't remember the exact number. And they will observe very few neutrinos. So you can see they observe 2000 neutrinos over a span of this many years. But what they found was that only 1/3 of the predicted solar electron neutrinos were observed in 1968. They gave their first result. So the question was that where are the missing solar neutrinos going? So the first conjecture was that the experiment is wrong, because it is difficult to detect a handful of argon atoms. I explained the procedure to you. You can see that it requires a lot of precision, and this is like whether everything is going correctly or not. That was a big question. Then some people said maybe the solar model calculations are wrong, because the solar neutrino flux was calculated based on some solar model. There are the fusion reactions, but to calculate the flux, you need the transport of the neutrinos through the sun and various other properties of the sun. And John Buckle was a pioneer in calculation of these standard solar models. And people said that maybe these are wrong, because too many things are going into that, which can give a wrong result. And the third option was that the solar neutrinos are getting converted to muon or tau neutrinos. And so that's why the experiment, which is sensitive only to the electron neutrinos, it is recording a shortfall of the events. New experiments were planned to check the above results. So the one of the experiment was the Kamiokande experiment, which was the predecessor of the Super Kamiokande experiment. And actually, the Kamiokande experiment was planned to test nucleon decay. So it is called the Kamioka nucleon decay experiment. And in what happens is there are some theories of particle physics in which one says that the proton is not stable and the proton can decay, and they wanted to study the proton decay. However, they realized that they can also study the solar neutrinos, and they can study the solar neutrinos using this neutrino electron scattering reaction. And this Kamiokande was a real-time detector. Like the chlorine experiment was not a real time because it is not recording a event by event basis. But Kamiokande could even, it was using a Cherenkov detector using photomultiplier tubes, and it can record an event, when the event comes, and it can show that it is studying the direction of the event. It showed that the neutrinos are indeed coming from the sun. So that they verified, but they also found that the rate is less. They observed half the electron neutrinos. So there were also the gallium experiments, which was also radiochemical experiments, which used slightly lower energy, which detected slightly lower energy solar neutrinos. But in all these experiments, it was found that the observed nu flux is less than theoretical prediction. So this yellow is the standard solar model prediction with some uncertainties, and this blue is the observed events. And what one can see is that, the observed event is less than the theoretical predictions, even including the uncertainties. In the gallium, the super Kamiokande, and the chlorine experiment, and all these experiments were sensitive to the electron neutrino. Kamiokande was sensitive to the other type of neutrinos, but with a reduced strength. So it did not have the statistical significance to collect the other type of neutrinos because it was observing them together. So it can do a study, but it was with a reduced strength. And this problem remained unsolved for 30 years. Finally, this problem was solved by the Sudbury Neutrino Observatory detector, or the SNOW detector as it is called in Canada. It used heavy water. Kamiokande used ordinary water. SNOW used heavy water. And what is the speciality of heavy water is that in heavy water, one can have a reaction which is for the electron neutrino with the deuterium, but it can also have a reaction where all three types of neutrinos, electron, muon, and the tau, will participate with equal strength. And it used 1 kiloton of heavy water, and it also had to go 7,000 feet underground, use 10,000 photomultiplier tubes. And what it observed was, it observed 1/3 electron type of neutrinos from this reaction. But in this reaction, they observed that the total flux is same as that predicted by the standard solar model. And this reaction has the electron neutrinos plus the mu and tau neutrinos. So if they combine these two reactions, then one can say that they have observed 2/3 mu and tau neutrinos. So they conclusively established that the solar electron neutrinos, by comparing these two reactions, that the solar electron neutrinos are getting converted to other neutrinos. Not only that, they also observed that this reaction, which is sensitive to all the three flavors, agreed with the standard solar model prediction. So the solution of the solar neutrino problem that was established by SNOW was that the neutrinos change themselves during their flight from sun to earth. So supposing I start with a flavor nu-e, one can compare it with some ice cream flavor, and then when it comes to the earth, it will become combination of the three flavors E, mu, tau. So it's a nice thing that, if you buy, say, a chocolate ice cream, and while you are walking towards your home, you get three flavors from that. So we would enjoy that, all the three flavors. However, this is also very, very useful that, this changing of flavors. And the scientists really are very much benefited from this thing to study the properties of the neutrinos. And so this was the thing that it was, one can say about this experiment, that the research group in Canada led by Arthur MacDonald could demonstrate that the neutrinos from the sun were not disappearing on their way to Earth. Instead, they were captured with a different identity when arriving to the Sudbury Neutrino Observatory. And this phenomena is known as neutrino oscillation, which is the one a neutrino can change its flavor after passing through a distance. And this is a quantum mechanical interference phenomena. So this is the solar neutrinos established that there is indeed oscillation of the solar neutrinos. Similar evidence also came from the atmospheric neutrinos. I mentioned earlier that the atmospheric neutrinos are produced when the cosmic rays react with the air molecules to produce pions and muons. And if you see this decay chain, then you can see that there are two nu mu and nu mu bar vis-a-vis one nu e. Like if a detector is, most of the detectors that I am considering here, they are not sensitive to they cannot distinguish between the particle and the antiparticle. So they measure a total nu mu and nu mu bar flux that I call as the nu mu flux. So what is expected nu mu to nu e ratio is 2:1. But what was observed by some of the detectors like Kamiokande, IMB, and this was observed to be less than 1. So what they gave is the ratio data by the Monte Carlo prediction, and this came to be less than 1. And however, some of the experiments said that no, this is close to 1. So that's why this was called the atmospheric neutrino anomaly. Some of the experiments are saying that the nu mu's are converting, and the question is what is happening to the muon neutrinos if these experiments are correct. But some of the experiments also said no, there is no such anomaly. So the Super Kamiokande detector put a resolution to this anomaly, and Super Kamiokande, as I said, is the largest underground neutrino detector in the world. And I said that it observes the solar electron neutrinos through the neutrino electron scattering, but it also observed the atmospheric neutrinos, which are at a higher energy range, through neutrino nucleon interaction. And what did it observe? So this is a view graph which shows the, the geometry of the problem. So this is, say, the Super Kamiokande detector, and we have the cosmic ray neutrinos coming from all directions, and this is isotropic, and they can reach the detector from passing through about 20 kilometers. So these are called the downward neutrinos, or reach the passing through the earth about 10,000 kilometers. These are called the upgoing neutrinos. Now, the cosmic ray flux is up-down symmetric. However, if there is neutrino oscillation, then what happens is that the neutrinos which are passing through short distance will not oscillate, but neutrinos which could pass through the long distance, they could convert and they could oscillate. So they wanted to test that whether the conversion that was observed, the shortfall that in the ratio that was observed by the Kamiokande detector is due to oscillation or not. For that, they built a detector. The Kamiokande was 5 kiloton, Super Kamiokande was 50 kiloton. So they study the zenith angle dependence of the event. So the zenith angle is the angle made with this imaginary z-axis at the detector. So they study the zenith angle dependence of the events, and they can measure the flux of the downgoing and the upgoing events, and can compare the flux and see if there is an up-down asymmetry. And indeed, they observe the up-down asymmetry, which can be seen from here. This is the cos theta. So this is the graph presented by Takaki Kajita from Super Kamiokande collaboration in 1998. So this blue is the theoretical prediction, which is up-down asymmetric. This is the symmetric. This is the expected events. This is the number of muon neutrino events. What they observe is that this red, they are observing these red points, and this green is the 2-generation nu mu nu tau oscillation. So if they say nu mu is oscillating to nu tau, then one gets the green curve, and you can see that the green curve fits the data so very well. So this established nu mu nu tau oscillation and solution to the atmospheric neutrino anomaly. This was confirmed later by accelerator neutrino experiments in Japan and US. And so what we see is that the solar neutrino oscillations was due to oscillations of nu e to nu mu and nu tau. And these conversions actually take place inside the solar matter. I didn't get into the details, but they actually take place inside the solar matter, where the neutrinos have some kind of tiny interaction with the solar matter, but which has some effect on the neutrino conversion. So the solar neutrino problem is due to conversion of electron neutrinos to the muon and tau neutrinos. And the atmospheric neutrino problem can be solved due to the conversion of the new muon neutrinos to the tau neutrinos. And the solar neutrino problem was also confirmed later by the Camland reactor neutrino experiment. So these astrophysical sources have some uncertainties because one is calculating the fluxes based on some model. But for the reactor and the accelerator man-made sources, we know the flux well. So it is important to get independent confirmation of these results. And scientists have indeed obtained that. So the neutrino oscillation is a very, very established field now. And the 2015 Nobel Prize was awarded to Takaki Kajita of Super Kamiokande collaboration and Arthur MacDonald of Sudbury Neutrino Observatory collaboration for discovery of neutrino oscillation, which shows that neutrinos have mass. So this is the Nobel citation. The Nobel Prize in Physics 2015 recognizes Takaki Kajita in Japan and Arthur MacDonald in Canada for their key contributions to the experiments, which demonstrated that neutrinos change identities. This metamorphosis requires that neutrinos have mass. The discovery has changed our understanding of the innermost workings of matter and can prove crucial to our view of the universe. So this is due to, as I say, neutrino oscillation, and neutrino oscillation requires, it's a quantum mechanical phenomena, interference phenomena, which requires that neutrinos have mass and the different flavors of neutrinos mix among themselves. When the Pauli postulated the neutrino, it was thought it is massless. The standard model of particle physics, which describes all the known fundamental particles and their interactions very well, assumes the neutrinos to be massless. However, this discovery of neutrino oscillation established that neutrinos have mass, and so one has to look beyond the physics, beyond the standard model. So that's why this is a very, very important discovery, because it gives us a window to study the physics beyond the standard model. So, in India also there is the India-based Neutrino Observatory proposal, which is a detector for atmospheric neutrinos. Remember, the first observation of the atmospheric neutrinos was in the Kolar gold mine in India. So we thought that, we should have a neutrino detector in India, and it was the proposed detector is a 50 kiloton magnetized iron detector. The speciality of this detector is it can distinguish the neutrinos from antineutrinos. As I said earlier, the Super Kamiokande detector cannot distinguish the neutrinos from the antineutrinos. However, this iron detector can distinguish between the neutrinos and antineutrinos, and this gives us a good sensitivity to the ordering, how the mass states are ordered. I have the 3 neutrino states. I know now that they are massive, but there is an ordering issue. And the INO experiment has very, very good sensitivity to the mass ordering. Of course, many of you may be knowing that it ran into rough water because of environmental issues. It has to be started in 2002, 2001, but it had to change the site due to some environmental issues, and it is still struggling with all that. But it is a very, very good project. So now I discussed about the atmospheric neutrinos, the solar and the supernova neutrinos, which are MEV neutrinos, atmospheric neutrinos, which can be GeV energy. However, I also said that there can be neutrinos from other astrophysical objects, and they are of much higher energy. And these kind of objects are, for instance, the active galactic nuclei, which is a compact region at the center of galaxy with a high luminosity, and they are very luminous sources of electromagnetic radiation. Or the gamma ray bursts, the sudden intense flashes of gamma rays, which these are extremely energetic events. And this is slightly old. We are having more information about these gamma ray bursts now with this gravitational wave observation also. Now the question which was asked, this was a much before that, whether they also emit neutrinos, and the question is how to detect that very high energy neutrinos. For this, the IceCube neutrino telescope was, and it is still running, it was started in the Amundsen Scott South Pole Station. So what it said is that, we need a huge volume. So this is a kilometer cube detector. and it used the ice. So we have seen that the super Kamiokande detector is a water detector, but the idea was whether one can use the ice to detect the neutrinos. So one has to put these strings, and see there, this is a deep core which has more strings, and they have these sensors, the optical modules, and they have the photomultiplier tubes. And so this is the ice slab, and this is a kilometer cube detector. This is a gigaton ice detector. And this experiment has indeed given it has observed the ultra high energy neutrinos in 2013. After I think 7 years of running, it first gave the few neutrinos events which are around PV energy. These were called the Bart and Ernie. This color code is due to different arrival times of these events. And so far they have isolated more than 100 high energy cosmic neutrinos with energies between 100 TeV and 10 PeV. So TeV is 10 to the 9 GeV, this is 10 to the 12 GeV, from more than a million atmospheric neutrinos and hundreds of million cosmic remyons. So they have observed now many high energy cosmic neutrino events. And they have also initiated the era of multi-messenger astronomy using neutrinos. So there was an event in 2017 that IceCube has observed in, which is called IC170992, and it could be correlated with a flaring blazar observation in using some gamma ray telescope. And these results, that was in 2018, this and 2017-18, this correlation was established, and these results constitute the first ever identification of a likely source of extragalactic neutrinos and of high energy cosmic rays. So this is the first first that that these high energy neutrinos are coming from blazars, which are type of AGNs, active galactic nuclei. And so IceCube, and this is called the multi-messenger astronomy, that one can detect astrophysical objects in more than one signal. For instance, neutrinos, cosmic rays, gamma rays. One also knows that with gravitational wave, gamma rays and neutrinos, that when LIGO observed the neutron star merger, that was related to some gamma ray observation from the Fermi telescope. And however, there was no correlation with the IceCube neutrino events found in that. The importance of neutrinos is that neutrinos have no bending in magnetic fields. They are not charged particles, so that can point back to the source. And they have minimal scattering, so can arrive directly from the regions from where light cannot come, as I have emphasized earlier also. This is for the TeV, PeV neutrinos, but for higher energy neutrinos, for instance, greater than 10 to the 16 EV neutrinos, there is the ANITA experiment, which is an array of radio antennas attached to a balloon, and which flies over Antarctic ice sheet, and they aim to detect ultra high energy neutrinos. So these neutrinos will interact with the ice, and they emit some radio waves, and these are detected by ANITA through some effect. And this is and ANITA has reported 2 events which have no explanation, which have found no explanation in the standard theories. And so this has also generated a lot of papers, the ANITA anomaly, but it's only 2 events. So one is not sure that whether there are also, it could also be some problem with the experiment, the interaction with our understanding of the interaction in the ice, etc. So with this, I will come to the end of my lecture, that what I have tried to convince you is that the neutrinos are everywhere, but they hardly interact with matter, and detecting them requires huge detectors. But because they are weakly interacting, they carry information from deep inside stars, and especially the IceCube observations have made the neutrino astronomy through high energy observation of high energy neutrinos is a reality. And one has also initiated the multi-messenger astronomy through the neutrinos. Neutrinos have many unique properties, like I said, the mass and mixing for which creates the oscillation. There are other unique properties, and these can hold the key to our understanding of the nature. So I will end with a quote by Robert Frost, that but outer space, at least this far, for all the fuss of the populace, stays more popular than populous. Thank you.
Thank you. Professor Goswami. I think we are slightly ahead of time. So I will request Dr. Roy now.
Yes, Professor Goswami, please thank you for your presentation, especially on this biography of Neutrino. Uh, and now we have few questions. Please, would you please stop the sharing the screen so that we can uh, just stop sharing the screen? Okay. So we have questions. Uh, Let me ask some questions. First, start with Dr. Sudipto Mojumdar. He asked that cross-section versus energy graph is smooth apart from the sharp change
Yes.
at the extragalactic origin. What does it mean? Can you hear me?
The cross section increases with energy, but so when we are detecting, then the flux reduces with energy. So because if you see the flux, then the flux is reduces with the energy. If you check the neutrino flux, the cosmic microwave background, which has the lowest energy, that has the highest flux, because these are coming from very far. The high energy astrophysical neutrinos are coming from very far.
Okay. So next question is from Dr. Tanushree Sahu. Could you please brief us about the fundamental differences between neutrino and antineutrino, with special mention about left-handedness and right-handedness?
Uh, like yes, like they have different helicities actually. So in the standard model, we know that the neutrinos are left-handed and the antineutrinos are right-handed. And because neutrinos are massless, the handedness is related to the helicity. So for right-handed, the spin is in the direction of momentum, and for the left-handed, the spin is opposite to the direction of the momentum.
Thank you. Our next question is from Dr. Soumik Ghosh. He asked that would you please explain a brief about the supernova explosion?
Yes, the supernova explosion occurs like when first when we have the energy balance, that the radiate this the this when the so in supernova, what happens is the heavy nucleus is created, and this we have this the fusion, the radiation, this radiation pressure, the balances the gravitational pressure. However, when we are above the Chandrasekhar limit, then there is a collapse, and then what happens is that so then the star starts collapsing, and then the inside of the star becomes a shock wave is generated, and the inside of the star becomes a neutron star, and the outside is ejected as the supernova explosion. In fact, neutrinos play a big role in pushing this shock wave forward. So in the explosion, this shock wave, which is generated at the when there is the fall of the matter, then at the boundaries these shock waves are generated because of matters of different densities, and the shock wave actually stalls in supernova simulations, and the neutrinos play a big role in pushing the shock and in causing the explosion.
Two more questions. One is from Dr. Imran Ali. He wants to know how Cherenkov theory is related to detection of neutrino.
No, so what happens is that that if the when the electrons are passing through the water, then they can emit Cherenkov light if their velocity in the medium is greater than the velocity in vacuum, and that's what happens in the water. So they emit this Cherenkov radiation, because you can calculate the angle, and you can see that they can emit the Cherenkov radiation, and that that's how, and that is what is detected in the water because it is passing through the medium water. So it emits the Cherenkov radiation, and that is the that radiation triggers the photomultiplier tubes.
Okay, thank you. Another question from Dr. Paulo Brai Gupto. He asked that neutrinos are taken as the best candidate for Majorana fermion, and what can be the possible process to prove that?
So yes, I did not mention about this, and neutrinos are Majorana fermion. So Majorana fermion is a fermion which is its own antiparticle, and because neutrinos are neutral particles, supposing if I have a charged particle uh, as its own antiparticle, then the charge conservation will be violated. However, neutrinos are neutral. It has no electric charge, so it can be its own antiparticle. But as I said that the neutrinos are lepton, but so the neutrinos and antineutrinos have opposite lepton number. But this lepton number is not really a symmetry, which is dictated by a theory. So the lepton number can be violated. So the neutrinos are the best candidate for the Majorana fermions, and it means that the lepton number is violated. So the Majorana nature of the neutrinos can be established in processes where the lepton number is violated. And these processes are called the neutrinoless double beta decay processes. And what is that process? That, there are double beta decay processes observed where the double beta decay is energetically more favored than the single beta decay. So nucleus goes to another nucleus with Z minus 2 and emits 2 beta particles. Now, what happens is that this reaction conserves lepton number. However, if there is a violation of lepton number, then there is a finite possibility that there will be and it emits the 2 neutrinos. However, if it is a violation of lepton number, then there is a possibility that these 2 neutrinos will not be emitted. That's why they are called the neutrinoless double beta decay. It is a very weak, rare process. So it has a small cross section, but there are a lot of experiments which are working on observing neutrinoless double beta decay. There are so far no experiment has observed. There was some when we were in during our PhD, some experiment said, or just after our PhD said that they have observed the neutrinoless double beta decay, but it was not conclusively established later. So far one has not observed it, but there are lifetimes. They give bound on the lifetimes of the process, and people are trying to improve that bound more and more. So this is one of the topics on which I work a lot, neutrinoless double beta decays theoretical implications.
Another few questions are there. Can I ask?
Please.
I think there is time. You can ask at least one more question.
Okay. So undergraduate student or Abhishek has asked that how do you know that which neutrino particle is emitted by different celestial objects? Does black hole emit neutrino?
So, for instance, as I said, the solar neutrinos, the super Kamiokande experiment or the Kamiokande experiment could measure the direction, and it said that it is coming from the sun. Now, for the different astrophysical objects, there are, that's why I said about this multi-messenger astronomy, that the neutrinos will point towards a source, because you can trace, for instance, ice cube is also a Cherenkov detector. So for the Cherenkov detector, you can point towards the source. And from other observations, you can know that if there is a point source there. For instance, if you see that this experiment which they could correlate with a blazar, so that was from the gamma ray, I think the magic telescope, some other telescope also showed that there is a gamma ray burst, and they could correlate that the neutrino came from that gamma ray burst. So that gave the that is the first observation, that the neutrino is coming from that source. So you can direct the neutrino towards a point source, and then you have to see if there is a point source. But for the gravitational, for the black holes, as I said, that the gravitational wave observation could not correlate any event with the neutrinos so far, so we don't yet know.
Another question is from Dr. Arnab Sarkar. Can neutrino travel beyond the speed of light?
No, it cannot. There was one experiment called Opera experiment, which few years back gave some experimental result that neutrinos travel higher than the speed of light. However, later it was proved that the experimental results were not correct. So that is not possible.
And the final question, no more questions will be asked. This is the why are neutrinos always in motion? This was asked by Anubhav Saha.
We are as we are considering neutrinos are the ultra relativistic particles. Neutrino mass is very, very small. So these are ultra relativistic particles. So their velocity is much more than the mass of their mass.
Okay, thank you very much, Professor Goswami. Now I pass to Professor Sinha to continue this program.
Okay, thank you, Dr. Roy, and thank you, Professor Goswami, for a very informative and interesting talk. And if some of the people want a little break, then we can take it. Otherwise, if Professor Dattagupta is ready for the next hour and so, then we can start right away.
I'm ready.
Okay, so let me introduce the second speaker of today and this afternoon. Professor Shushanto Dattagupta, a distinguished physicist. I have known him for a long, long time, and his research interests have been in non-equilibrium statistical mechanics and condensed matter physics. Though he wrote it the other way, he wrote first condensed matter physics and then non-equilibrium statistical mechanics. I changed the order. The reason is, in fact, some of his work and interest in non-equilibrium statistical mechanics helped me in studying the mathematically foundational quantum mechanical questions, which has not been, I think, well studied, even till today, I dare say. And it is not a complete theory as a mathematically understood object. In the context of that, at least I will be quite interested in what he has to say, though I guess he will be addressing a kind of a different audience today. And Professor Dattagupta, aside from being a distinguished physicist, has held many other distinguished positions as well in his career, including being the director of S.N. Bose Center for Basic Sciences in Kolkata, then founding director of the Indian Institute of Science, Education and Research in Kolkata, though it is actually in Kalyani, and was also the vice chancellor of Vishwabharati University earlier. And I have the pleasure to request him to speak, and his topic today is, can graphene be used to teach quantum mechanics? Professor Dattagupta.
Thank you very much, Professor Sinha, for this very, very kind introduction. I would also like to thank you, the Indian Academy of Sciences, and also in particular, Dr. Manoj Roy from Brahmananda Keshab Chandra College for making this talk possible. I must add also in my thanking list, Dr. Shubhankar Vishwas. I haven't met him earlier, but I want to remind him that he actually helped me in drawing some pictures for a resonance article. And so in my next trip to Bengaluru, it will be a pleasure to meet Shubhankar as well. So now, sorry for this interruption. So, and also thanks to Brahmananda Keshab Chandra College and the principal for hosting this event. Manoj, am I visible?
Yes, Prof. Yeah.
Yeah. So this is Shubhankar, right?
Yes.
Okay. So, and then finally, to all my young participants, because these talks are meant for the students. And for me, the students may range from actually high school, from class 11, 12, to undergraduates, to postgraduate, and then perhaps try to bring them to some exciting stuff that is going on in the research areas in modern condensed matter physics. Now, there's a proverb in Chinese called "a picture is worth 1,000 words." I would like to twist that proverb and say that equations are worth 1,000 words. So in my talk, unlike the previous one, I plead with the students that there will be more equations, but I'd like to wade through them with your help carefully and with some patience from your side. So with this background, let me just tell you that, and Manus, can you help me in projecting the first slide, please?
Yes, just share the screen and
share the screen.
You have opened the file?
Yeah.
Open the PDF file. Now share the screen.
I have shared the screen.
It is not shared yet.
I'm sorry, I don't know. Open the file meaning?
No, you just scroll down this browser. Scroll down this browser and scroll down to the.
No, it's on the left tab. Prof, you have to, yeah.
Just minimize it, sir.
Minimize it, sir.
Is that okay? No.
You minimize this browser and then open the PDF file.
All right. Sorry for this delay, but let me just get a handle of this.
Just minimize it. It is not minimized yet.
I have to open the file first, right?
Okay.
Sorry for this little hiccup in the beginning. You want me to open the file, right, Manas?
Yes.
Just 1 second. Is it okay now?
Now you have to minimize.
I've opened the file.
You have to minimize the browser. It was appearing the browser only.
Minimize. Restore down or?
Restore down.
Sorry. Is it visible now? I can't see anything now. Sorry.
Just open the PDF file only.
Huh?
No, Manus, first of all, sir, please stop share.
Stop share, sir.
Stop sharing option, just click on that.
Stop share?
Stop
Yes.
sharing.
Okay.
Yeah. Now share again. Now share screen.
Now share screen, sir.
And select the PDF file.
And select the PDF file. Which one you want to share?
Let me listen to first to Vankor. So I now go to my file, right?
Just a moment, Prof. Manoj, do you have the PDF file the professor has sent to you?
Yes, I have.
Why don't you open it on your screen? Why don't you open it on your screen and share? And while the prof talks, he will ask for the next slide. You do that.
That's what I thought Manoj will do.
Yes, Manoj, why don't you do
Should I
that?
it?
Yeah,
Okay.
yeah. Open the file on your screen. Yeah.
Okay, then. Okay.
And share your screen. And the prof, while he speaks, you keep scrolling down.
Okay, just
Yeah. Okay.
Okay.
Manoj, you said that's what you will do, so I was depending on that process.
Let's do that, Manoj.
Okay.
Yeah, yeah. That's good.
Yeah, it is now okay.
Yeah, Prof, you can start now, Prof.
Right. So I'm sorry to the fellow participants for this hiccup. So the title of the talk is, can graphene be used to teach quantum mechanics? Now, let me give you a background. See, all of you are so internet savvy these days, and you must have done a lot of Google search and all that. You'll find out that graphene is considered to be a material of the future. It's a wonder material with many properties: mechanical, electrical, magnetic, biological. It is as a biosensor. It's got unusual transport property. So you're excited because this may have possibilities for quantum information storage, in quantum computing, and lots of other things, even including catalysis. So now it turns out, however, that every attribute of graphene has to be understood by using quantum mechanics. Quantum mechanics in the non-relativistic arena, as well as quantum mechanics of relativistic type, given to us by Dirac and others. So let me go to the next slide now. So what is graphene? Graphene is just a single layer of graphite, which is a collection of carbon atoms. You can see from the structure, you have what you may call a honeycomb lattice. A honeycomb lattice is a hexagonal structure. And in fact, you can think of a honeycomb lattice as broken up into triangular lattices, two interpenetrating triangular lattices, because if you join every alternate sides, you will get an equilateral triangle, and all these structural properties will come into the fore as we proceed. It's a two-dimensional material. It's considered to be one of the thinnest ones, and also because the interlayer distance is much smaller than the intralayer dimensions. Graphene is viewed as a nanomaterial. As you know, that there's a lot of interest in nanosystems in the present times because of the fact that you can use them in quantum devices. Quantum devices they are everywhere, in your cell phone, in your computer, etc., etc. It's also a highly conducting material. Let me go to the next slide, please. Now comes some undergraduate and, in fact, high school stuff. While interacting with high school students, I found out that in your class 11, class 12 CBSE syllabus, you have exposure to, let's say, the electronic structure of a single carbon atom. And this is, in fact, there in the chemistry syllabus. So, as you know, a carbon atom, sorry, you're going too fast, Manus. Manus, I didn't want that. Yeah, just hold on to this. So, a carbon atom, as you know, has 6 electrons. Out of these, and so now the question is, how do you distribute these 6 electrons? So here comes quantum mechanics. This goes back to Niels Bohr in 1913, and just as in the case of the you try to think of how to adjust these 6 electrons of carbon. Bohr said that there is something called a principal quantum number, call it n, and the distribution is something like 2n squared. So if an n takes all kinds of integer values, 1, 2, 3, etc. So if n is 1, then you have 2 possibilities, because then n squared is 1. If n is 2, then of course you have 2 squared is 4, but because electrons have spins, which we'll discuss later on, you have 8 possibilities, and so on and so forth. So therefore, the first 2 electrons if n is equal to 1, so that is my first entry as 1s. So 1 stands for n equal to 1. And if n is equal to 1, there's something called the orbital angular momentum, L, and L then can be only 0. So therefore, we denote it by S. So we have what is called a 1s state, and you put 2 electrons there. You can put 2 because you know that there's this, though there is a spin, you know that you can put 2 electrons of opposite spin in the same quantum state. But these 2 electrons are very, very close to the nucleus, and they are called core electrons. They do not really participate in any transport or any thermodynamic property. So we'll ignore them. We are now left with 4 electrons out of these 6. So how do you distribute these 4 electrons? And here comes your first step that you learn in high school quantum mechanics. That, you know, these 4s electrons will go into a superposed quantum state. So what is the meaning of superposition? You see, quantum mechanics says that a particle like an electron is not just a particle, it's also a wave. And you understood it also from the ideas of photoelectric effect when Einstein explained in 1905 that what you have is light falling on a metal and then electrons are ejected. And in order to explain this phenomenon, he had to propose that light, which up till that point was considered to be an electromagnetic wave, in fact consists of, I'm sorry, most wire shifting my view. So it's a wave, and it consists of corpuscles or photons. So it's a particle like a photon, or it's also like an electromagnetic wave. So this duality is very important for quantum mechanics. And a wave, as you know, is extended. So you can have many possibilities. So you have quantum states. So now, therefore, you distribute these 4 electrons. And how do you distribute them? Now you have gone into n equal to 2 state. And so L can be equal to actually also 1. So you have not only L equal to 0 or S state, you can also have L equal to 1, namely P state. The P state configuration, however, is not spherically symmetric, unlike the S state. So you see, therefore, you can have a 2s electron and then 3 2p electrons. You might have said, well, I could have put 2 electrons in the 2s state. There's something called Hund's rule, which again, because of the exclusion principle, says that 2 electrons would rather stay a little apart. And so, therefore, 1 electron goes to the 2s state, and 2 other electrons go into the 2px and 2py. What are x and y? Of course, x and y are arbitrary. Later, you'll see that my xy plane is going to be synonymous with the plane of graphene, the 2-dimensional plane. So I have a 2-dimensional plane of xy, and then a z direction jutting out normally. So therefore, you have now a 2s electron juxtaposed with 2p electrons in the 2px and 2py. And on the right, you see that they form what is called a sigma orbital. Again, it is coming superposition of quantum states. What is an orbital? An orbital is a graphical description of the possibility of finding a quantum particle at a given point, because as you know, a quantum particle is represented by a wave function, and it's the mod square of that wave function gives you the probability of finding a particle at a given point x. So you have these 3 butterfly-like objects which are at relative orientation of 120 degrees, which you can see at the corner of this graph. And these are called sigma orbitals. So these lie in the xy plane. And why are this called sigma? Because you go back to the Greek vocabulary, where sigma stands for S, and S like as you said earlier, has symmetry. In this case, the symmetry is about the z-axis, which is transverse to the xy plane. So these three orbitals are symmetric. So that takes care of my 3 electrons. What happens to the fourth? The fourth one goes in a state which is called a pi orbital, which is given at the right-hand top corner. The pi orbital, however, is in the 2pz state, and it therefore the z direction is elongated along the z direction, and it is normal to the xy plane. All this, my fellow students will realize that they have learned it from class 11, class 12 chemistry. Now, this is the electronic configuration of a single carbon atom. Having done that, we'll now like to switch gear and introduce you to some elementary quantum mechanics, which you learn partly in the high school, because you will see that all I'll deal with will be 2 by 2 matrices, which you learn in mathematics also, and then some elementary quantum mechanics like Schrödinger equation, etc., etc. And then I will take you slowly to undergraduate and postgraduate syllabi, where you learn about matrices, Dirac notation, etc., etc. So as we go on, I'd like to explain all these steps very carefully with you. So may I have the next slide, please? All right. So this is something that I already have said. I need not repeat. You already heard about positron in the previous lecture. You heard about the neutrinos. So these are quantum particles. They cannot be localized in consonance also with the uncertainty relation. And then, all these things that I have written down here are already said before in my talk. So let me now go to the next slide. Yeah. So this is now a little bit of algebra. Please bear with me. Because after all, if you want to learn about quantum mechanics, you have to know a little bit of mathematics. So all that is being discussed here are properties of 2 by 2 matrices. How do they come along? If you remember in the history of science, quantum mechanics was developed from 1900 actually, from Planck's work on the black body radiation. Then came 1905, Einstein's work on photoelectric effect, and also special theory of relativity in the same year, which we'll come back to later. And 1913 is Bohr. Then 1921 is Louis de Broglie, who talked about the uncertainty relation and the fact that associated with any particle, you have a de Broglie wave, lambda, which is given by the Planck constant divided by the momentum. And then very fast developments. Heisenberg gave the matrix formulation of quantum mechanics in 1925. Schrödinger gave a wave equation for quantum in 1926. And then finally Dirac from 1920 to 1930. We'll come back to Dirac later on. But in between, there was a very interesting experiment by Stern and Gerlach, who showed that, for instance, silver ions, when they are pushed through inhomogeneous magnets, on the screen you found 2 spots. And so surmise was, and that was propounded as a theory by Gauss-Schmidt and Uhlenbeck around 1926, that the electrons, which is in the outermost orbit of the silver ions, has a spin, as an internal attribute. This is an intrinsic property of the particle, and that actually interacts with the magnetic field, and that interaction is like in the Zeeman effect. It actually causes a splitting, especially because the inhomogeneous magnetic field makes it like this interaction like an inhomogeneous force, and that force causes an acceleration, and the 2 particle beams get split on the screen. So now, how to explain these 2 states? You already heard in the previous talk about Wolfgang Pauli, who proposed neutrino, to call it neutron at that stage. So it's a 2-state system. So a 2-state object, either you can represent by a spin S, or Pauli introduced another convenient notation sigma, given by the top relationship. And now these sigma matrices are these 3 by 3 matrices given here. You can see that sigma z, this is again a convention. If you choose your z as the axis of quantization, then sigma z is diagonal. It has got these two elements, 1 and -1, corresponding to the fact that the corresponding spin operator, spin value can have two possibilities, plus h bar over 2 or minus h bar over 2, where h is a Planck constant, h bar is h divided by 2 pi, as we find it to be convenient to write it in that way. Associated with sigma z, also there are this sigma x and sigma y. Now, there is this statement in quantum mechanics that if you can measure sigma z, then sigma x and sigma y become uncertain. They cannot be measured simultaneously. And this uncertainty is reflected in the fact that if you work in a representation in which sigma z is diagonal, then sigma x and sigma y will not be diagonal, as is given here. In fact, you find out by just very little algebra that these matrices have this commutation properties, and they also have an anti-commutation property, that sigma x, sigma y plus sigma y, sigma x, etc. will be equal to 0. So that makes them very special, as we'll see later. So this is just the property of sigma matrices that you probably learn in your first course in quantum mechanics. Now the point is that if along with sigma x, sigma y, and sigma z, you introduce also the unit matrix, which is what? It is a diagonal matrix which has elements 1 and +1 now. Sigma x, sigma y, sigma z, and the unit matrix form a complete set in this two-dimensional Hilbert space. So any 2 by 2 matrix, you can try it out, can be written as a linear combination of these 4 matrices: sigma x, sigma y, sigma z, and 1. That's view graph case. Right. Now, how to write down the corresponding wave functions? Because see, Heisenberg said that sigma, which is an operator, is now represented by a 2 by 2 matrix. And of course, an operator is an observable sigma z, observed like in Stern-Gerlach experiment. Now, an operator has to operate on something. So therefore, a matrix to operate is actually a column matrix. So the two column vectors have these elements 1, 0, and 0, 1. And you can, it's just a simple task for my high school friends that you take these 2 by 2 matrices like sigma z and operate them on these column matrices, and you'll find that the eigenvalue, these are eigenfunctions, and the eigenvalues are 1 and -1 respectively, corresponding to the fact that the spin of the electron is plus h bar by 2 or minus h bar. So as I said before, now you switch your mind. Though I'm talking about a real spin of an electron or a proton or neutrino, as you heard last talk, any 2 by 2 state. What can be any 2 by 2 state? Like 2 levels in quantum optics, 2 levels, or the 2 positions of a particle moving in double wave. They all can be represented by this Pauli spin algebra, and that makes it mathematically very attractive, as we'll see later. We'll see now when we move from this 2 by 2 Pauli spin description to graphene, you'll find that these 2 states do not correspond to real spin of the electron, but the possibility that the electron, especially the pi electron, which is in the 2pz state, lying normal to the plane, can, however, either in one of these 3 triangular lattices, one of these sides or the other. So there are 2 possibilities, and it is these 2 possibilities which will be mapped by your Pauli spin matrices. So let's proceed now again. Go to the next slide. All right. Now, if you now think of graphene or any lattice, you have a particle which can occupy a lattice side, but it can also be a quantum particle. So it quickly then moves to another side. This phenomenon is called tunneling, because you don't need thermal energy to go over a barrier, because it's a wave function. The particle wave has a tail and it moves from one side to the other. So how do you make this possible within your Pauli spin terminologies? What you construct is a P plus minus operator, which is given on the top of this slide. It has got this matrix representation, and you can easily work it out that if you start from a plus state, this P plus minus operator, will make the plus state move into the minus state and vice versa. It will not do anything to between a plus state and a plus state, or a minus state and a minus state. Those elements will be zero. So I think there's a mistake here. So from minus to plus, you'll again get 1 as you get this. Oh, sorry. Because the way it is constructed, it only kills a particle in a minus state and bring it to the plus state. And that's why the last entry is 1. All other entries are equal to 0. So therefore, as we said before, in a two-state system, which can be arbitrary, it is not necessarily just a spin-half quantum particle, but two possibilities. A quantum particle is visualized to move from one state to the other, which could be like the left to the right state of a double well, or could be the two states of a qubit. As you know, these qubits are used as elementary inputs in quantum computing. It's like two quantum dots. And so if you represent one dot by the plus state and the other dot by the minus state, you can transfer information from one to the other. And if you can do that quantum mechanically, then that's called coherent transfer of information. And this is the object of quantum computing. However, of course, and this is not the area that I'm going to cover today, which is what was alluded very kindly by Professor Sinha, that any such small object like a dot or a nanosystem or like a graphene will be invariably in contact with the environment, and the environment brings in, the environment could be that consisting of other electrons, other phonons, other quantum mechanical objects, and they actually introduce what are called quantum dissipation effects, and that is, in fact, the area in which Professor Sinha is an expert on stochastic quantum mechanics, but that's not what we will talk about today. Those problems are also very interesting for graphene, and they will take us to a really modern research level problems. But let's now constrain ourselves to this simple discussion of quantum mechanics of graphene. So may I have the next slide, please, Manush? Okay, I switch gear. And now again, I take my student participants to 1900 and then 1905. You see, in 1905, Einstein, in addition to giving the theory of the photoelectric effect and the black body radiation, for which he got the Nobel Prize, he also worked on what is called the special theory of relativity. He said that abandon the notion of classical physics, where classical physics says that the energy E, kinetic energy, is given by p squared over 2m, where p is the mechanical momentum. He said that if a particle has mass, it's called the rest mass, even if it is even at rest, then there's an energy associated with it, which is called mc squared, where c is the speed of light. So the energy now is a combination of the kinematic momentum, which is given by p, and also the rest energy. So the energy is square root of mc squared plus cp squared. Now you see this is a very interesting phenomenon. It would define the velocity as you normally do by the derivative of the energy with respect to the momentum. You get this equation where you have a numerator Cp, and in the denominator you have this radical under the square root side. So you start plotting this velocity, which is dEdP, along the y-axis, and the momentum along the p-axis. Normally in classical physics, this will be a straight line. The velocity will be p over momentum. But not in relativity. In relativity, of course, v is 0 and p is 0. But when p is very, very large, namely the rest mass is very small, and particle is moving with relativistic speed, as you heard in the lecture by Professor Goswami, when neutrinos travel with extremely large speed, then you find out that the velocity is actually equal to c, the speed of light. So there's a range of these possibilities. So remember this relationship again. If the momentum is small, then you only have rest mass energy. If the rest mass energy is very small, then you're in the relativistic domain. You'll find that in graphene, very interesting. You must not think that the electrons in graphene, namely the pi electron that we talked about earlier, is moving with the speed of light. It's actually moving with what is called Fermi velocity, which is estimated to be 1/300 of the speed of light, but yet you'll have Dirac physics or you have relativistic physics, because it turns out that the physics that we'll be dealing with would correspond to rest mass equal to 0. So let's go to the next slide now. Okay, so this is a graphical description of what you have in the classical limit. In the classical limit, as we said, that the velocity is much smaller compared to c. So the dominant energy term E is p squared by 2m. So if you plot the energy versus p, you have this inverted parabola. All right. This is what you normally see. However, if the particle is massless, for instance, photon or neutrinos at one time were considered to be massless, but now you know, as Professor Goswami had said, that there are also massive neutrinos, those mass is very small. But if you have a massless particle like a photon, then the energy where p is, energy versus p has this cone structure. It's near p equal to 0. The energy actually goes like the speed of light times the mod of p. So this, as you'll see, is called a Dirac. And this Dirac cone has very interesting physical consequences for graphene. So here the velocity, the speed of light, and energy momentum relation is not quadratic, unlike classical physics. It's actually linear in the momentum, and this linearity will have strong consequences for graphene, as we'll see momentarily. Next paragraph, please. Manush. Yeah. So let me remind you of how you get the Schrödinger equation. So okay, backtrack a little bit. So you have quantum mechanics, which got developed up till 1926, as we said, thanks to Heisenberg and Schrödinger and earlier Niels Bohr. And then you have this Einstein's theory of relativity. How do you reconcile the two? How do you bring in relativity, special theory type, also in quantum mechanics? And this was the challenge before the British physicist Dirac. So let me just tell you what the problem is. So, in the Schrödinger formalism, the energy is like an operator. There is a Hamiltonian operator, which is a partial derivative with respect to time. E is IH bar ddt. Momentum is also an operator. It is minus IH bar times the nabla, which is the derivative operator with respect to the position. And therefore, if you have a free particle, you have, therefore, the solution of the Schrödinger equation is like a plane wave. You have e to the I k dot r, where k is the wave vector, minus I omega t, where omega is the frequency. And then you get this free particle Schrödinger equation, because what you do is for energy E, you substitute IH bar ddt, and for P, you substitute minus IH bar nabla, and that's how you get this free particle Schrödinger equation. Now, what did Einstein say? Einstein said that, like, position is not absolute. You have Galilean transformation. Position changes as you move from one frame to the other. Time is also not absolute. Time also transforms. And this transformation is given by what's called the Lorentz transformation. So position and time have to be treated on the same footing. If time is appearing in linear form in the Schrödinger equation and space is appearing in quadratic form, this symmetry is lost. So you must have this symmetry preserved. So one way of handling this was due to Klein and Gordon, and he wrote down this equation, which is second order in time and second order in space, and therefore it satisfies this position-time duality and symmetry. However, there's a problem with this Klein-Gordon equation, problem with conservation of particles. Dirac came up with an ingenious idea that why can't I now think of a linear equation which is also linear in time derivative and linear in spatial derivative. And as you'll see, this ties up with Einstein's relativity, because in the extreme relativistic limit, energy is linear in momentum, as we saw in the last view graph. And if it's linear in momentum, then the momentum operator will be simply one derivative and not a quadratic derivative like in Laplace square, but the dx or delta itself. So that's what is shown in the next view graph. All right. So now the issue, however, is so now you see we physicists, especially the theorists, try to put Planck constant equal to 1, speed of light equal to 1, because you see, well, these are unnecessary baggages that you don't want to carry. So you have the energy squared. Now it's given as px squared plus py squared, okay, plus m squared. You know that you had c squared earlier and c4. I put all that equal to 1. So how to get the square root of that? So here is the one scheme of doing it, which is what Dirac did. That suppose you think of px squared, py squared plus m squared as an operator, okay, and you operate it on this 2 by 2 unit matrix. A unit matrix has diagonal elements 1 and 1. Now you can verify, all of you can verify, just multiply these 2 by 2 matrices which have p, which is m and minus m in the diagonal, and px minus ipy and px plus ipy is Hermitian adjoint, Hermitian conjugate in the off diagonal terms, and you multiply the two and you get the left hand side, lo and behold. So now taking square root is easy. You can surmise, because the square root will be then this operator. And if you remember our Pauli spin matrices as we had introduced before, namely m and minus m will transform as m times sigma z, and px minus ipy in terms of sigma x and sigma y can be written like thus. So the square root of the energy is now actually px sigma x plus py sigma y plus m sigma z. Beautiful. So what you have therefore is that now these are like 2 by 2 matrices, and sigma x, sigma y, and sigma z. They are called Pauli spinors now. And so Dirac then wrote down simply from this symmetric consideration that he said that you have to, of course, follow the Schrödinger equation, but you also have to follow the space-time symmetry that was given in by Einstein, the theory of relativity. And so he wrote down this linear equation, which is also one, is one order in time derivative and one order in space derivatives. But then you introduce the sigma x, sigma y, and sigma z. So now, so what do these sigma x, sigma y, sigma z correspond to? In Dirac way of looking at things in 1928 to 1930, he wanted to incorporate what Stern and Dirac have measured and what Gauss-Schmidt and Uhlenbeck had proposed, that the electron has spin. So these are two state objects. So now you look at this this equation, which you may call the Dirac equation. However, now let me go back to a fundamental conservation principle of quantum mechanics. As you know, time has to be conserved. That is, all your microscopic equations, even in classical physics, Newtonian equations, Schrödinger equations, they must be invariant if you make t go to minus t, time going negative. So this is called t invariance. There's also, however, a parity invariance. I remember Professor Goswami talked about the beta decay. In beta decay, parity is not conserved. Namely, if you look at the mirror, you don't see just the mirrored reflection of yours. Your parity is not conserved if you change x to minus x. And along with that is also called charge conjugation. So the entire conservation principle is based on CPT, C for charge conjugation, P for parity, T for time reversal. Now, charge conjugation actually means, in mathematical terms, that you change I to minus I. You take conjugate, like in complex variables. So you see, IH bar will become minus IH bar, no problem for the first time. But if you want to absorb this negative sign and you make the Dirac equation also invariant on the charge conjugation, you have to put ms minus n. So what does it mean? So Dirac surmised that the negative mass will correspond to an antiparticle. If electron is a particle, then it must have an antiparticle called a positron, which you already saw in the last lecture. So now you have not only two spin states, so you have two states coming from the spin, the real spin, and also I'm getting interrupted by Mitra, who's doing some algebra with 2 by 2 matrix, which is fine. And so you have this 2 by 2 coming from the spin, and you also have another two possibilities coming from the fact that along with the electron, you can have a positron. You should see these are the glorious days of quantum mechanics. In fact, Gambo wrote a book called 30 Years That Shook Physics. So 30 years is 1900 to 1930, where Dirac is already proposing positron purely from symmetry considerations, though positron was actually discovered experimentally in 1932 by Anderson. So here is an example where theory was in fact ahead of experiment. So anyway, so now you have four possibilities, two coming from the real spin and two coming from the particle-antiparticle symmetry. We have the next slide, please. So I'm sorry, this is a very crowded view graph, but this is the last one that I'll bore you with. So you see, you have four possibilities. So you have to write four Schrodinger equations. What are these four possibilities? On the left-hand side, you will see a ket vector, which is a Dirac way of representing a state. So the first entry is an electron with an up spin. The arrow up pointing up represents a spin positive with the spatial coordinates of r and t. So the first entry is E, arrow up, r comma t. So on the right hand side, you'll have the first entry as coming from the rest mass energy, and the other entry is coming from your momentum terms, which however are linked with sigma x, sigma y, and sigma z. So this is now the Dirac equation, which you probably learn in your third course in quantum mechanics these days in the first year, second year of MSc perhaps, and in physics. And so then the next entry is for the electron with an arrow down, which is like the other spin component. And again, you have four terms on the right side. Then the last two equations correspond to the positron represented by pi, again with an arrow up, which is spin up, a positron with a spin up, positron with a spin down. And you have the possibility of conversion of a positron into an electron through this px minus ipy kind of a term, because as you saw that so these are this, it's called the Dirac C. You have positive mass and the negative mass, or the opposite mass. Positron, of course, as you know, has the same mass as the electron, but it has got an opposite charge. And so you incorporate all these things into these four equations, and these are called the Dirac equations. Sometimes you write them down in terms of the gamma matrices, but I don't want to go into that complication. So having more, so now you see, let's take stock of what we are doing. We first started out with the electronic configuration of a single carbon. And we used non-relativistic quantum mechanics, ideas of particle wave duality, ideas of superposition principle, and talked about the orbitals, the sigma orbitals, the pi orbitals, etc. So far, we have not come to graphene because you have to now put all these carbon atoms together and form a lattice. But before we did that, we now have covered some quantum mechanics, which is done in maybe 2-3 courses in quantum mechanics. We talked about the Pauli spin for two-state systems, and now we move from non-relativistic quantum mechanics to relativistic quantum mechanics by incorporating Einstein's special theory of relativity within the Schrödinger language, and came to this Dirac equation. So now you see your Hamiltonian. As you scroll down, you will see that in addition to a term which is the rest mass energy mc squared times an object called beta, which is actually in fact also a 4x4 matrix, where this unit matrix 1 is a 2x2 unit operator. This is 1 and minus 1, and along with that you have also a sigma matrix. As sigma is given here, c times sigma dot p, where sigma is the spin, as you remember, and p is the momentum operator, and sigma is called helicity. This came up in the question answer session in Professor Goswami's lecture. So you see, it is the scalar product or inner product of sigma with p. It's a projection of the spin into the direction of motion of the electron. So now if you have a particle like a neutrino, which was thought to be normally moving with the speed of light, then of course, if it is moving at the speed of light, then you cannot move in another frame which will be faster than that. So therefore you'll see the spin to be actually only, it's like a vector rotating, and it's only be like a left-handed vector or a right-handed vector, only one of them, and therefore this is called helicity, and it's also related to what is called chirality. These are all words which are used in high energy physics and relativistic quantum field theory. But you see, all these objects now, all these nomenclatures come into the play in a material science problem of graphene. So helicity plays an important role in the study of graphene and its thermal and transport properties. So with this much, now we have to move to graphene. So let me point out again that what is graphene? You take these carbon atoms and you form a lattice. This lattice turns out to have an hexagonal structure. It's called a honeycomb structure. It is two interpenetrating triangular lattices. And lo and behold, the symmetry of the triangular lattices is 120 degrees at angles with each other, and that comes from your sigma orbital. So here's this fantastic way quantum mechanics is operating. It's a structure of the sigma orbital, which was like a butterfly, or three wings of the butterfly at 120 degree orientations. When you form a lattice, those electronic energies are responsible for giving you the triangular lattice structure of graphene. Manas, may I have the next slide, please?
Sir, I am just going to interrupt you because audio, there is some discretization in your audio signal. Okay. So please, can you speak louder or close to the microphone, or you can use the another microphone using headphone.
I cannot use any other microphone at the middle of my lecture. So let me ask you if I'm more audible now.
Okay. Okay. Then carry on, please.
Yeah.
Yes, Prof. When you're bending a little closer, we can hear you perfectly.
Yeah. I understood, Shankar. So I'm coming a little closer.
Okay.
Sometimes gives more complicated instructions. Yeah.
Yeah. No. Okay.
Yeah. So, am I audible now, Shankar?
Yes. Yes. Perfectly, Prof.
Yeah. So I realized that I got excited because these lectures are best given on a blackboard with a chalk and duster.
Yes, I understand.
And used to more physical movements, and this technology stuff that you guys are more experts on are something that are beyond me. But anyway, please bear with me. But actually, it is Shubhankar's voice and Manas's voice which are cracking. Perhaps not mine.
Okay.
All right.
But you're pretty okay, Prof. Your voice is pretty okay now.
Shubhankar, do you imply that I should go back to my previous slides?
No. We could hear you. It's just that there are some crackling, static kind of noises. So.
Why is it that?
Okay.
But why is it that your voice is cracking so much now?
Could be bandwidth issues, Prof.
So I think it's a problem with BKC system.
No, but I can hear you perfectly. So you can actually go on. Okay. Now you're perfectly audible.
All right. So where are we? So we said that, so we want to talk about graphene now. And how does it tie up with the Dirac physics? So the point is that in graphene, you have an electron, either an electron at a site or no electron. No electron means a hole. So you think of a hole like an antiparticle because it's the absence of electron. It's like the positron. So in solid-state physics and condensed matter physics, a hole plays the role of the antiparticle of the electron, namely the positron. So that is the analogy we will make now. Second analogy is with the spin. In graphene, for the kind of physics we will discuss, the actual spin of the electron does not matter until now. What is a two-state system? A two-state system represents two possibilities. Either an electron is at one site or it is not in that site. It lives behind a hole. So these are the two states. And so these are the two sites. I'm sorry, I backtrack a little bit. So you have also two sites. One is, remember I said, and I'll show you some picture again, that a graphene is basically two interpenetrating triangular lattices. So we have an A sublattice and a B sublattice. So an electron can belong to an A sublattice, think of it as a spin up, or a B sublattice, think of an electron as a spin down. So it's not a real spin, it's just the two states of the lattice, plus the fact that the absence of electron will be like an antiparticle. In addition, graphene is a two-dimensional system. The Dirac equation that I wrote down was for a three-dimensional spatial system plus one-dimensional time. So it was a 3 plus 1. For graphene, we are talking about a 2 plus 1 dimensional physics. Two spatial dimension and time, of course, is the other dimension. So you ignore now PZ terms from your last four entries. You simply have PX and PY. In addition, if you recall that if the Dirac particle is moving with relativistic speed, then you can ignore the rest mass. If you ignore the rest mass, then of course the energy momentum relationship is linear, as you can see also by appearance of Px and Py in linear orders. These are called Weil fermions. Because Weil already talked about them in the context of actually neutrino, which was the subject of the previous lecture, because neutrinos were considered to be massless at that time. And so you see, because they were massless, they would move with the speed of light, and therefore you did not have to consider the rest mass energy. So you ignore also the first entry into this 4x4 equations that I got in the last view graph, and you now are in 2 dimensions. So you have these 4 equations. They are the cornerstone of all properties of graphene. Again, let me remind you that the electron is not actually moving with the speed of light in graphene. They're moving with a Fermi velocity, which is about 1/300 of the speed of light. And there is no positron here, but it's only a hole, because either I can have an electron or not an electron. And then you have two sides, which are the A and the B sublattices of the two triangular electrons. And Manush, please have the next slide, please. All right, these are the pictures that Shubhankar actually had helped me in drawing for my resonance article. So remember, you have these 3 sp2 orbitals, which are these sigma orbitals, the butterflies. This is given in figure A, and they have this symmetry of this 120-degree triangular lattice, an equilateral triangle. On the right-hand side in part B of the figure, you have the pi electrons, which are these circles projecting out of the plane, which are normal to this butterfly. So these sp2 orbitals in the plane, which are the sigma orbitals, is called hybridization, because it's like in my part of the world, mangoes are very abundant, and when the mango season is just over, and you form hybrids of mangoes. So you form now hybrids of orbitals, and these are called hybridization. sp2 notation has nothing to do with my earlier notation. The fact of sp2 orbital is only that you're hybridizing 1 2s electron with 2 pxpy electrons, and that's why it's an sp2 hybrid orbitals. But then you have an unhybridized p orbital, which is normal to the plane, and lo and behold, it is this unhybridized. While the sp2 hybridized orbitals are responsible for the structure, the solid state structure, it's a p orbital electron, the lone p electron, which actually keeps jumping back and forth from one lattice site to the other. We call it tunneling. It's all responsible for all the transport properties. Next view graph, please. So the hybridization that we talked about, and then again, this is quantum chemistry of high school undergraduate type, where you have these three orbitals which are written as a linear superposition of the Dirac states of 2s and 2py and 2px. And so you have to normalize them properly. That's what explains the square root 3 factors in the denominator. And you have therefore these three orbitals, spa2, spb2, spc2, which is a linear combination of 2s, 2px, and 2py, and they give you these hybridized orbitals, and they form. And now, if you form a lattice, you have a carbon atom with its nearest neighbor. It starts doing hand holding, and the hand holding is responsible for a bonding, and this is what is called a carbon-carbon double bond, as is shown pictorially in the figure downstairs, down below in this view graph. Okay, carry on, please. So, as we said already, I mean, this is now a superfluous view graph, but this is more pictorially describing that you see I've now split the honeycomb into a pink lattice, pink sublattice, and a green sublattice. Each of these pink or the green is in fact a triangular sublattice with 120-degree orientations, and the electron keeps hopping from one of the green sides to however the nearest neighbor side is the pink side. So you allow only for the time being nearest neighbor hops. That's the simplest approximation. These nearest neighbor hops of the electron from one side to the other are captured in solid state physics. Let's say if you look at a book by Cattell or Ashcroft and Mermin, which you study in your first course in solid state physics in masters in physics, you know it by the name of tight binding model. A tight binding model says that the electron is more or less localized at a site. Only occasionally it tunnels or it hops from one side to the other. So let's now introduce a tight binding model, and I'm almost coming to the end. I plead with your patience now for about 5 to 10 minutes now, maybe even less. And so let's go to the next view graph. So before that, a picture is worth 1,000 words. So what you do now, you form from a single carbon atom with that electronic structure of sigma orbitals and pi orbitals, sp2 hybridized orbitals, you form a lattice. So when you form a lattice, you then try to calculate energy versus momentum. This is called dispersion relation. When you do that, remember we said that this pz electron, we actually could have put in one more electron there, because exclusion principle, thanks again to Pauli and Fermi, would allow you, this is called Fermi-Dirac statistics, would allow you to put another electron. But there's only one electron, so it is actually a lone electron. And it is hankering for a pair. It doesn't have a pair. And so this is reflected when you calculate the band structure or the energy dispersion. You will have a you have a conduction band and a valence band. The conduction band is depicted by gray color and the valence band is depicted by blue. So the valence band is completely occupied, reflecting the fact that there's one pz electron per site, and the conduction band normally is totally unoccupied. Now, you know from solid state physics, it is these conduction electron guys which are responsible for all thermodynamics and transport properties. So somehow you have to promote the electrons from the valence to the conduction band. In this case, as it turns out, that these blue bands touch the gray bands in 6 different places. These are called the Dirac points. And out of these 6, there are 2 which are inequivalent, but I've now shown you only one on the right-hand side. So you see, the point at which the conduction and the valence band touch, there the gap goes to 0. If there's no gap, then you can easily promote an electron from the valence to the conduction band. And this gap is depicted now at the tip of what is called a Dirac cone. And why is it a cone? Because if you remember, in the extreme relativistic case, the energy momentum relation is linear. You may ask me the question, sir, what is extreme relativistic case in graphene? There's nothing like that. It's just that fact that, as you will see in the next view graph, in a little set of algebra, that when you calculate the tight binding model dispersion energy, you get linear term in the momentum. So let's go to the next view graph. So see, if you remember, I can straight away go to the mathematical expressions. You have a class state corresponding to the presence of an electron at a site I, which is a suffix I. And that I may belong to an A sublattice, which is one of the, that's a pink triangular sublattice, or a B sublattice, which may be the green sublattice. And you have 2 possibilities, a spin up and a spin down. Now you have a translationally invariant 2-dimensional system. For any translationally invariant system, you do what is called a Fourier transform. This is something that you learn in mathematics, maybe in your first course in functional analysis or something like that. And so you write down the states in terms of this what I call the block states, using Fourier transformation, exploiting the fact that translational invariance is there, and therefore the momentum is conserved. Momentum is a good quantum number. What is Ri? Ri is a position vector for the electron at its site, and similarly for Rj, while K and K prime are called the wave vectors. The wave vectors is basically the momentum P divided by the Planck constant h bar. Now, as I said, in the tight binding model, you assume that you are only allowing nearest neighbor hops. So Rj and Ry must be related by a vector delta, which is the nearest neighbor vector delta defined by the last entry into this view graph. Let's go to the next slide now. So now you have to form, just as you form an sp2 hybridized state, you form a hybrid of an electron to be there or not there in the next, to be not there or not there. And these are called symmetric and anti-symmetric combinations. And these are actually called in chemistry the bonding and anti-bonding states of Pauli. Here's a little bit of history again. In an old man, I like to tell you about history. While quantum mechanics was having its glorious days of theoretical physics from 1900 to 1930, came 2 people. One of them is Linus Pauling, who came to Göttingen and learned quantum mechanics from the feet of Max Born. And then there was also another person called Van Vleck, a Dutch physicist, chemist. Pauling, of course, got the Nobel Prize in chemistry for, I think, vitamin C. So he's primarily a chemist. And he understood quantum mechanics and he applied to the idea of bonding. And so he, in fact, wrote The Nature of the Chemical Bond around 1935, where he imbibed all these things about quantum mechanics, just as Van Vleck did around the same time, who wrote a book on magnetism and spectroscopy called Electric and Magnetic Susceptibilities. So you see, these ideas go back to bonding and anti-bonding states of Pauling. which are then responsible also for giving the structure of benzene and things like that. So we are talking about actually interdisciplinary science. So there's no distinction between your mathematics of 2x2 matrices, physics of quantum mechanics, non-relativistic, relativistic, chemistry, quantum chemistry, and materials. They all come together in this laboratory of graphene, and therefore it's called a wonder laboratory. So now you have the tight binding model, which is given in this view graph where the Hamiltonian has the T term, which is a transverse term, transfer term, which I put outside the summation as a constant, it's an assumption. And you have this projection operators P that I had introduced earlier. These projection operators will transfer an electron from the ith A sublattice site to a jth B sublattice site, and Hermitian adjoint, which is what the Hamiltonian must be, will make another complex conjugate term possible, and you sum over all possibilities of I and j over all the lattice sites. If you then rewrite these things in terms of the Fourier transform, as we mentioned, then you get a dispersion energy relation, energy momentum, which is Ek given by last entry in this view graph, plus or minus square root of the mod of T of k squared. So what is T of k is what you now should carry out in graphene, and then that is done in the next view graph. So all that you have to do is a bit of algebra. These are all given in my resonance articles, which, as I mentioned, that Shavankar knows about. And so you need these basis vectors that you learn in the Kittel solid state physics called the Bravais vectors, and the reciprocal lattice vectors, the B's and the B1s and B2s. You need three nearest neighbor vectors, delta 1, delta 2, delta 3, fanning out like three butterflies, and then the corresponding vectors in the K space, which will give you the Dirac points, the K and the K prime vectors. So I'm flashing them through, but you can read them in my resonance article that I'll momentarily give a reference to. And so, I mean, there's no point in your following all the details of how from this A1, B1, delta 1, and K, you actually calculate T of K. When you do that, and you come near k equal to 0, because if you remember your solid state physics, most of the electrons are within the Fermi sphere, but those electrons which are just off the Fermi sphere, called electron hole excitations, and they're the ones who are responsible for all transport and thermodynamic properties of low energy electrons in solid state physics, and they are near k equal to 0. So we have to expand this T of k near k equal to 0. And you do that, lo and behold, you get a Dirac physics coming. Next view. So I therefore have come to the end. This is the concluding slide. So when you then calculate this T of k, and you have the full dispersion relation, which is what you saw in terms of the green and the gray band structures. But now you come close to k equal to 0 point. This is called one of the Dirac points, around which all the all the business takes place. You expand the T of k, you find the energy and momentum relation is linear. So it is this linearity of the energy and momentum relation which is analogous. It's metaphorically analogous. It's a paradigm of Dirac physics. It's the linearity of the energy momentum relationship, which is responsible for all the exotic and exciting material properties of graphene. So most of the quantum mechanical concepts, if I sum up, employed here are in the high school plus 2 syllabus, although they're scattered. Ideas and orbitals, bonding, Schrödinger equation, electron orbitals, they all find places in chemistry, as my class 11, class 12 students will certify. Then rudimentary notions of relativity in physics and then appear in physics. 2x2 matrices appear in mathematics, and you bring all these themes together in graphene. Finally, it ought to be stressed once again that graphene, calling it a Dirac solid, is only metaphorical. The actual electrons in graphene neither have zero mass nor do they travel with the speed of light. What is amazing is that certain predictions of relativistic quantum mechanics, which have so far eluded experimental verifications, even in the context of neutrinos, invisible neutrinos or visible, whatever, neutrinos from the sky or black holes, everything, these are all important there, but it's very difficult to do experiments. But graphene is a material which you can actually create in the laboratory by what is called a Scotch tape technique, which is what Geim and Novoselic did, for which for graphene, they got the Nobel Prize, I think, in early 2002 maybe. So it's amazing that those predictions of relativistic quantum mechanics, which have so far eluded experimental verifications, now find justifications and applications in the down-to-earth laboratory of graphene. So once again, I would like to thank Professor Sinha, the Indian Academy, and also Suvankar Viswas and Dr. Manoj Roy, and also Brahmananda, Keshab, Chandra. Let me just give you a flavor of the references I have here. Every kid in quantum chemistry and physical chemistry learns it from the book by P.W. Atkins. It's called P.W. Atkins Physical Chemistry, Oxford University Press. It's my first reference. Then all the exciting experimental properties of graphene have been covered in a resonance article. As you know, resonance is published by the Indian Academy of Sciences, under whose auspices we're having this lecture today. And in this resonance articles, all are meant to be student friendly. And there's an article by Mandar Deshmukh and a student at the Tata Institute in Mumbai called An Exciting Two-Dimensional Material for Science and Technology. All these issues of carbon hybridization and to tight binding to Dirac solid is something that I have discussed in resonance in the January issue of this year. And so now you scroll down, and if you go to the last slide, and I talked about Pauling. He wrote a book called The Nature of the Chemical Bond, which is republished by Cornell University in 1960. And every other entry is mostly a textbook like Kittel, solid state physics, Schiff, quantum mechanics, all of you are aware of. And Schrödinger's original papers in quantum mechanics, where you get the wave equation, is given as a fourth reference on this view graph, and an illuminative discussion, the Stern-Gerlach experiment, which put a seal on the spin of the electron, is given in a book by French and Taylor. And my last view graph, Manoj, please. Is Manoj there? Okay. And they're all, you can see, they're all textbooks. I mean, whatever statistical mechanics I have used in the context of Pauli exclusion principle and Dirac statistics are given in Huang's book on statistical mechanics. Messiah quantum mechanics deals with the Pauli spins. Dirac, the great book he wrote in 1958 edition of Oxford University Press, talks about the bracket notations that I talked about, and also the Dirac equation, which is covered also in Sakurai's book in quantum mechanics, modern quantum mechanics. Metz-Packard deals with two-level systems as they're mapping with the spin half. And the last reference, the last but one, are these classic papers by Dirac on the Dirac equation. And the very last entry is on positive electron, or the positron, which is a physical review of Anderson in 1932. I thank you all once again for your kind attention.
May I add here, for the benefit of all the students, that the professor quoted some resonance articles, and the benefit of for all the students is that all the resonance, since its publication from the very beginning till the latest issue, they are all available free online on the Academy website. You can check it out. The articles that the professor referred to, you can find them online for free.
Yes. And Suvankar, let me just add this, the last issue of Current Science on 25th August has an article of mine called Can Graphene Be Used to Teach Quantum Mechanics, which is what the subject matter of today's talk is. The last 25th August issue of Current Science. Also,
so that's the latest
Indian
one.
Academy.
That's the latest one, isn't it? Yeah. Okay.
That's right. Yes.
Okay,
Right.
so I think we thank Professor Attogusto for a very interesting talk. And I think now I will request Dr. Roy to organize the question and answers.
So, Professor Sinha, after 2.5 hours, everybody's voice seems to be cracking.
I hope some people have the energy and everything to ask a few questions.
I think Manus has to fix
Sir,
it.
okay, sir. Let's start the question answer. I am just accumulating the questions.
Voice is going in discrete quantum states.
Okay. Now you can hear me?
Yeah, Manas, we can hear you.
Okay. So one question from Shambhu Mitro. We are doing calculations in presentation in which sigma z is diagonal.
Yes. Yes. Because you have to assume a representation in which one of the three non-commuting operators is diagonal. You could have chosen a representation in which sigma x is diagonal or sigma y is diagonal. The meaning is that you chose to measure the spin along the z-axis by putting a magnetic field. This is the old measurement problem in quantum mechanics. When you put a magnetic field along the z, you have what is called a collapse. And so you measure sigma z only. You have no idea of what sigma x and sigma y are.
Okay. Then
And mathematically, therefore, you say that sigma z is diagonal, while sigma x and sigma y are off diagonal.
another question is from an undergraduate student that what does the different value of spin means?
See, the point is that the different values means two different projections. Remember the Stern-Gerlach experiment, in which you had sent a beam of silver ions through inhomogeneous magnetic fields, and the beam splits into two. So these two beams which hit the screen correspond to the only two possibilities. So all your fundamental particles, which are called fermions, because they obey the Pauli exclusion principle and Fermi-Dirac statistics, they are all spin-half objects, not just electron, positron, neutrinos, as Shubhavati Goswami had discussed, proton, neutron. So though Fermi-Dirac statistics would allow for all half-integer spins, in nature, in terms of fundamental particles, you have not seen anything other than a spin half, and that's why 2. In solid state physics, of course, you have composite entities which can have higher, like spin 3 halves, spin 5 halves, etc. But these are like composite particles. Now, I must also say that along with the fermions, you have also the bosons, which obey the Bose-Einstein statistics. They have integer spins, like the photon. And the famous Higgs boson has a spin 0. Photon has a spin 1. And then now we're talking about graviton, because the gravity wave, issue of the gravity waves being detected, and they have spin 2. So they have integer spins. We are talking about a different kind of an entity, one half of world's fundamental particles. These are called fermions, and they are just spin half entities or spin 3 halves, but only spin halves are considered to be fundamental particles, and that's why only 2 spin states.
Okay.
Professor, one question,
yes.
Manas, sorry. This is a question that I have been holding on for many years. So let me ask you your personal opinion. Graphene was supposed to revolutionize. I mean, we have been hearing about developments in graphene, research in graphene.
Replacing silicon.
Yes, and we were hoping that, I mean, the world was expecting that all these discoveries, all these research will lead to complete revolution, in the next, this would be the next wave. So what, in your opinion, as a researcher, do you think that why it didn't, go to the extent that we were hoping or expecting that it would eventually lead to?
I don't know the answer to why. Perhaps there are, I mean, you have to do some other technological thing with graphene, like, Shwankar, you already know perhaps that you have this, we're talking about gapless fermions now, but there's gapped fermions. You create another layer, And so all these things people are doing. I really cannot predict whether it will really replace silicon in all its glories, but it seems to have rather nice applications so far. What the future holds in store is something I don't know. I mean, maybe, for instance, I am now working on oxide materials. They also, you take two heterostructures of oxides, and they have all kinds of fascinating properties. So maybe while doing this fundamental studies, you also could come up with some other materials which will have other exotic properties and put into applications. This is what you are asking. That I really don't know what the future holds for us. Yeah.
Okay, thanks for sharing that. I mean, you're in theoretical physics, so we were hoping that that would translate into the next, the technological.
Is that a dig at the theoretical physicists that you're
No,
taking?
absolutely not. Because you're the people who pioneered this. So it's the technology people, the engineers, who should take the next step. So I was asking for your opinion why that didn't happen. Do you think there is some barrier between, getting the technology?
COVID-19 is a huge barrier.
Okay. But it is getting us to adapt to all this technology, isn't it? It's great to have you talk to us directly, face to face.
Yeah, I wish I could give a blackboard lecture, but anyway.
Yeah, we shall have that too once we come out of this situation. Professor Sinha will make sure that we can do this. Professor Sinha, can you unmute your speaker and speak a few words, please?
Yeah, what I am saying is that let Manas end the regular questions, and then we'll. Okay, Dr. Roy.
Okay, thank you, sir. The next question is the P plus minus operator is basically meant to explain the transformation of positron to an electron.
Well, if you think of positron to be representing a spin up and electron to be a spin down, you could do that. You could think of two sublattice positions. It will transfer something from one side to the other. Any two-state system, you can think of a two-level atom like in a laser, and you can transfer from an excited level to a ground level. Any two-state object, or you can think of tunneling in a double well, which is discussed in the book by, let's say, Merzbacher quantum mechanics. So if you make a particle move from one side to the other, like you have in a hydrogen in a lattice, so anything you can, that is the beauty of mathematics, that of these 2x2 projection operators.
There is another question, that is Dirac point is like a direct band gap in graphene.
No, the band gap goes to zero at the Dirac point. The Dirac point is a point, if energy is linear in the magnitude of the wave vector, then at k equal to 0, the energy goes to 0. So energy gap disappears. So the gap actually disappears in that Dirac point.
Okay. So another question, what are some most advantageous applications of graphene today?
Well, as we said in the first biograph itself, that and as Shubhankar has alluded to, that it's apart from catalysis in chemistry, apart from biosensors, today quantum mechanics is getting very exciting. Professor Sinha is very much knowledgeable about formal quantum mechanics. But today, quantum mechanics is coming at the realm of laboratory. You can have a single atom trapped and do its experimental study. You can have a two-level system do its experiment, like a qubit. You can do experimental study. So nanosystems also are therefore very exciting. And so one of the challenges, and Dr. Subhankar Biswas already was talking about these things, is in the area of what is called quantum computing. See, what is quantum computing? You see, classical computing is like Tarataka, like we used to send telegraph, is one or the other, okay? It's like a telegraph process, as in stochastic theory we talk about. But so it's like a two-state possibility, yes or no. But since you have superposition of a plus state with minus state, like we saw in the case of bonding and anti-bonding, depends on what kind of amplitudes you put in front of these Dirac kits. So depending on the values of these amplitudes, you can cover an innumerably large number of quantum states. So you can store quantum information to a large extent. That's why the great attraction of quantum computing is. But as Professor Sinha said in the outset, that a small system is invariably in contact with its environment, have dissipative effects, have what you call friction in classical mechanics, but you have quantum friction now. And they actually cause decoherence in these coherently evolving quantum systems. And the challenge, the technological challenge also is to how to minimize decoherence so that these things can be made into possibility of a quantum device where quantum computing and quantum information storage will be possible. So for my mind, that is the most exciting application of graphene, although of course from a biology point of view or from a materials point of view or from a chemistry point of view, you have other applications.
So we are formally stopping here. Question answer session now. Professor Sinha, please say a few words.
There are no other questions?
No other questions, I think. Yeah.
There seems to be another question. Is there any?
Okay. One question is okay. Our undergraduate student asked that what is quantum teleportation?
Yeah, this is what I find out when I go and teach in schools also. The school students today are so Google savvy and they get excited by space travel, teleportation, etc., etc. Actually, I don't know the answer to great detail, but I would imagine from the English meaning of teleportation, you transfer something from one state to the other. And this is done by projection operators in quantum mechanics. I don't know the fancier meaning of teleportation.
Okay, I think let us draw a curtain to this event, which has been extremely successful. I thank Professor Dattagupta for an interesting lecture, and also I thank Professor Goswami for an earlier very interesting lecture. So now I think Shubhankar can say a few words and close the event.
He says, thank you. Can you please discuss the further research options related to this topic? So if anybody can give a good answer, it would encourage some students to take up this. Very,
You mean
very exciting.
neutrino or graphene?
I think he's talking about graphene, research in graphene.
Okay. Well, so Imran, you know that this two-dimensionality of the system like graphene and many other heterostructures has given rise to an exciting world of what are called topological phase transitions. And that also actually was honored by a Nobel Prize a couple of years ago to Haldane and also to Thouless and Kosterlitz. And so these are exciting theoretical areas of quantum phase. As you know, that it's the phase of the electron, which is, or the phase of the wave function that is responsible for interference, for coherence and all that. Now, there are all kinds of interesting phases. If you have a magnetic field, then you have what is called the Aharonov bomb phase. And so that comes in simply because the vector potential has an influence on the possibilities of electron interference, even though the magnetic field does not intersect the electron path. Addition to that, and it has got no magnetic field context, but simply topology, it's called the Berry phase. So the dimensionality and the way quantum mechanics of these systems is carried out gives rise to very, very interesting effects of where this phase, either the Aharonov bomb phase or the Berry phase come into play, and they are responsible for many exciting physical properties. And if Imran gets in touch with me on through email or something today, of course, it's not possible to physically meet. I don't know where Imran is. And so I could give maybe other references where we can start a discussion.
That's good. Imran and all the other students listening, you can also check out the Indian Academy of Sciences website. We have internship programs, summer internship programs where students are sent to different labs across the country, and they work with people like Professor Datta Gupta and Professor Shinha, all the Academy fellows. They do take on interns to help in the research in their labs. So you can check out the Indian Academy of Sciences website at the internship program.
Yeah,
And
Professor
there'll be many other.
Thank you, Shivankar, for bringing this up, because Professor Murthy just wrote such a mail to all of us. Yeah.
So thanks everybody for participating, for joining in. My sincere thanks to Professor Datta Gupta and Dr. Goswami for making this such a really, I think illuminating is the word. We had a lot of questions and a lot of doubts got cleared about these two topics. And both of them are actually very now, in the research frontier, they have tremendous applications in what we are going to do now in the next 5 to 10 years and even in the coming decades. So people who are interested should really try to get in touch with these kind of people.
Maybe you can make our emails accessible to the participants.
Yes, Manush, could you do that in your from the feedback form? If you can have some kind of link to where the student can access how to get in touch for further questions in research and things like that.
Okay.
Yeah. Okay. So thanks a lot to Manush, to Professor Datta Gupta, Professor Goswami, and our outreach committee chair, Professor K.B. Shinha. Thanks a lot for coming aboard and spending a lot of time with us to all this to benefit all the student community and even people like myself who have questions and curiosity all the time. Thanks to Brahmananda Keshab Chandra College. We hope that we'll have further opportunity for collaborating with your institution again. Manos, if you want to say a few words on behalf of BKC, please do so.
Okay. On behalf of BKC College.
Maybe you should say who was Brahmananda Keshab Chandra first.
Okay, that will be in another session because he was a pioneer in Bengal Revolution, especially along with Raja Ram Mohan Rai. He was the founder of Brahmo Samaj in Kolkata. So, in memory of Professor Brahmananda Keshab Chandra Sen, our college was established.
And Professor Sinha and I have roamed around in Keshab Chandra Street of Calcutta many years ago.
Well.
Okay.
Yeah.
Then
say something about the college.
Okay, we are in. Yes. Our Brahmananda Keshab Chandra College is a college established in 1956 in the northern part of Kolkata. It was not Kolkata at the time, it was Boranagar, just opposite to Indian Statistical Institute.
Where Professor Sinha was the director of.
Yes.
And even Professor Partha Mojumdar is also
the president of the academy, also belongs to ISI. Yes.
So it's very
ISI should be expanded as Indian Statistical Institute. It may have different connotations otherwise.
Yes, our previous late Professor Dijas Datta Mojumdar was president of our college. Unfortunately, he passed away. So we have a very deep relationship with Indian Statistical Institute from very long time, and we have few faculties also from this ISI, first out graduate students as our faculty. So this was the college was established to flourish the education in the northern or suburb region of Kolkata. Earlier it was very famous academically. Still now it is continuing its legacy. But it is a very good environment and ecological background in this college. A huge lake of hundreds of acres of land as Bonhugli Lake. So it is a very pleasant atmosphere in our college and very peaceful as well. So most of the time we hear about that all colleges have some student disputes and all those things. But college it is very peaceful, very academic, uh, and research oriented as well. So what I can say more about patronizing my college, I should not speak more about it because you have to find it out. Now, on behalf of BKC College and the entire organization of this program, let me call it the fraternity of science and academic. Here we are here together, and on my own behalf, extend my heartily vote of thanks to all speakers, especially Professor Goswami and Professor Dattagupta and Professor K.B. Sinha. We are very fortunate that they have agreed to organize along with us this webinar for gracing your important work and sharing with your findings and your opportunities in Academy of Sciences. So it is a very good experience today, and we are very much thankful to all participants, all co-hosts, and part of our physics department, our IQAC team, and especially our principal, and everyone whoever is present here. So I thank you all. So just I am finishing my speech now. Please, uh, if you anyone just end it, please, Professor Kebishina, just end it formally.
Okay, thank you all, and well, let us close this now. Thank you.
Thank you all.
Thank you.